concrete about some methods which might be able to exploit some of those ideas discussed in the first part of the session. So the kind of particular framework I'll talk about in the second part of the talk, something that we called the Auxilary Pseudo-Marginal Mcmc method. So we kind of described this more kind of general framework within this paper, Pseudo-Marginal Size Sampling by Ian Murray and myself. And the basic idea is to take an original pseudo-marginal Metropolis Hastings type system and split the update on that kind of joint target density that we introduced in the previous part into separate Markov kernels which update those auxiliary variables and then the target variables of interest, these Z variables. So I'm just going to define this auxiliary pseudo-marginal Markov transition as just the composition of some transition operator which leaves this joint distribution invariant and varies only those auxiliary variables, and then a second one applied sequentially which just targets the Z variables, so the actual unknowns of interest in the problem. So I will use this naming convention throughout. That will, particularly in experiments, use this shorthand APM for auxiliary pseudo-marginal, and then two different acronyms to describe the two different operators, Markov transition operators, defining this T1 and T2 transition kernels. So for example, I will use MI for Metropolis independence, algorithms, M8 for Metropolis Hastings, and SS for slice sampling. So one particularly kind of simple variant of this auxiliary pseudo-marginal framework is this auxiliary pseudo-marginal Metropolis independence plus Metropolis Hastings algorithm. So this kind of looks a lot like the standard pseudo-marginal method. But basically, we're kind of splitting the standard pseudo-marginal Metropolis Hastings update into two separate accept steps. So we first define a proposal kernel which just updates the U variables, and here we're just going to define that as specified in the name as a Metropolis independence kernel on those U's, which just samples from this row distribution we met earlier. So the nice thing about that is, again, this is the operation that we know that we can do, and it's not kind of making any particularly stronger assumptions about our estimate or our problem. So we sample U variables. In this case, again, we'll kind of get this fortuitous calculation in the Metropolis accept between the kind of random-Nicotin derivatives of this density, such that the overall accept probability just becomes the ratio of the density estimates at the same Z with the new proposed U variables and the previous values. So we're kind of keeping Z constant here. And then we're just going to apply a standard Metropolis Hastings transition then to the Z variables, but here now keeping U fixed. So again, the nice thing about this is because we're not varying U here, we don't need to have explicit access to it, and we don't need to have access in particular to its density, or even though, say, its dimensionality. We just need to be able to compute density estimates and evaluate this kind of standard Metropolis Hastings kernel acceptance probability. So straight away we can see that it might seem that this is going to be intrinsically less efficient than the pseudo-marginal Metropolis Hastings method, because in every overall update formed by the concatenation of these two individual updates, we're going to have to evaluate this density estimator twice at least. So once in this Metropolis independence transition, one new evaluation at these new U variables, and then again we're going to have to evaluate it in the second Metropolis Hastings transition on the Z's at the new Z values. So if this is the kind of key cost in our algorithm, then we've kind of introduced this factor of 2, and it's not clear we really buy anything from this. But empirically, at least, we found that this kind of particular kind of clamped idea of clamping the random number variables, the auxiliary variables within this Metropolis-Hastings transition, and independently proposing them in some separate transition, often can define kind of more robust and efficient algorithms in practice. And the kind of intuition behind that is that we're separating out the two different issues at hand here. So typically, in pseudo-marginal methods, we may have some density estimator, which, as we said, may be high variance, which kind of implicitly defines that there is strong dependence between these u and z variables. And so in that case, this metropolis independence transition is likely to have a poor probability of acceptance. We're kind of doing what we know in general in Mcmc method is a bad idea. We're taking some potentially very high dimensional variable and then just independently proposing a new value from it independent of the current state. And so in high dimensions, we would generally expect this to have quite a poor probability of acceptance unless the target distribution was well matched by that independence proposal. So this kind of will be affected in some sense by the properties of the estimator and how well, how kind of low variance or how strongly coupled these z and u variables are. In this Metropolis-Hastings kernel, we're now into a much more kind of familiar terrain of a kind of standard Metropolis-Hastings setup. So for fixed u, this just defines some conditional distribution on the z's, which, although it may be complex, is it doesn't have that kind of slightly unusual form that we have in the kind of normal pseudo-marginal Metropolis-Hastings update. So we're just kind of pretably updating the z's, and we're not at the same time independently updating the u's. And so providing we make this proposal small enough or local enough in some sense, we should imagine that we'll be able to make this acceptance probability be at some target level. And so that's definitely not the case in the original pseudo-marginal Metropolis-Hastings method, where even if we make kind of very small moves, if we have a very poor estimator, we still may again get pathologically low acceptance rates. And this makes it very hard to, say, tune adaptively the parameters of the proposal kernel, because it's mixing together both the effect of the estimator and then the kind of broader kind of Mcmc tuning problem of setting the scales of this proposal kernel to match the scales of the target distribution. So yeah, just to kind of summarize, the nice thing about this is that modulo a little bit of extra work in needing to be able to somehow manipulate the state of the random number generator, which goes into the density estimator. So if, as a kind of minimal assumption, we think we can record the state of that random number generator at each stage in the algorithm and potentially alter that state to restore a previous pseudo-random number generator state on, say, a rejection. Beyond that, we don't need to know anything further about the actual random numbers which go into the auxiliary variables which form the estimate. So this is a little bit of kind of a faff implementationally, but it's a fairly weak assumption about how much information we have about the estimator. We need to be able to have access somehow to the random number generator which is used in it under the hood. So as I said, a key disadvantage from a potentially computational efficiency perspective is that we're going to have to evaluate this estimator twice for every overall joint update. But as I said, empirically, and I'll justify this with the experiments later on in this part, we found that this kind of very simple adjustment to the standard pseudo-marginal Metropolis-Hastings methods can often lead to quite considerable improvements in efficiency, and also significantly simplifies the tuning of the kind of Metropolis-Hastings part of the kernel. So the idea here, we kind of subsequently discovered after first putting up the pseudo-marginal slice sampling paper on archive, is very closely linked to a point raised in the discussion of the particle Mcmc read paper by Lee and Holmes, where they kind of exactly suggest this idea of separating the updates of the auxiliary variables within some density estimator and the updates to the actual target variables of interest. So we're not necessarily claiming this is at all novel, but it's more kind of an empirical point that in practice we found that this, in certain settings at least, can, for a very minimal change in the underlying algorithm that you're using, give quite a lot of improvements in usability. So as I said, I'm going to kind of step through in the level of complexity, both I'm assuming in how much information I can evaluate about this kind of joint target density, and in particular information I have about the auxiliary variables, to kind of propose more and more potentially complex but also hopefully efficient MCMC algorithms on this joint space. So one particular problem we might imagine if we're trying to define more general proposals to update the auxiliary variables is that often we have very little kind of intuition about those variables. We don't have kind of any geometric sense about what would form a good proposal to them. There might be a very large number of these variables, and we're probably going to, or at least in a lot of settings, it might seem unlikely that we're going to be able to, finely tune some Metropolis Hastings method to adaptively kind of suit the geometry of that auxiliary variables distribution. So one kind of obvious choice of something that we could do is use some sort of adaptive MCMC method. Rather than using some sort of like vanishing adaptation or kind of related variant, there is this class of algorithms that a lot of you will be familiar with called slice sampling, which does in some sense a kind of adaptive MCMC type update, but it does it all within the context of a kind of standard Markov chain multi-column method. So we're not having to kind of make any additional assumptions about the history of adaptation or so on. And this the slice sampling idea is actually broader and earlier than this particular analysis statistics paper by Radford Neal. So the kind of auxiliary variable formulation that's used within that paper, as well as underpinning things like rejection sampling, is actually used in other kind of slice sampling type methods previously. But the paper by Neal, I think, was perhaps the most kind of generally useful slice sampling type algorithm, is often what is associated with him in practice. So the slice sampling is not really one single algorithm, but a kind of whole family of them. But they generally share this property that they're able to propose quite large, bold moves within the target space, but then exponentially back off from these by making a series of Fever likelihood evaluations until they're able to accept some point, which if we make some very minimal assumptions on the smoothness of the target distribution so that we're not kind of having these point-wise singularities in our distribution, should always lead to some potentially very small but non-zero move that is accepted. So there's this kind of idea that slice samplers are often rejection-free methods. So it's worth noting right from the start that the kind of overhead in constructing this slightly more complex transition kernel, and in particular the need within it to make multiple evaluations of the density of interest, will typically mean that if we do know a lot about our problem and we're able to, say, propose some well-tuned random walk metropolis method, or even some more intelligent Metropolis Hastings proposal, and that's adapted to the specific target distribution of interest, that will probably perform better than slice sampling. So slice sampling is not a panacea. Its main advantage is, I would say, it's a fairly black box way of getting reasonable performance and being fairly robust to the choice of the few tweak parameters that it has. So, and we'll see that bear out in practice in the experiment. So there's kind of this one key parameter within the slice sampling algorithm, which is the initial slice bracket width. And we'll see later on that we can choose quite a wide range of values for this parameter and still get very close to optimal performance in practice. So, so far I've been kind of very hands-off about describing what slice sampling involves. If you haven't come across slice sampling before, this is unlikely to really kind of completely make you understand what the fundamentals of the algorithm are, but I'll at least try and give some intuition about the various different parts of the algorithm, because it will be important to considering later on why it's quite a useful algorithm to use in practice in the pseudo-marginal setting. So the kind of key construction which gives the algorithm its name is this idea of defining a slice for your target distribution. So the auxiliary variable construction which underlies all size sampling methods is that we define some auxiliary height variable as having a uniform distribution between 0 and the value of the density at the current target variable. So here, say u is our target variables. This h variable will have a conditional distribution which is uniform between 0 and r of u. And so we've basically taken in the, say, 2D case, sorry, a 1D density case, we've taken our original distribution defined on the real line, say. We're now defining a distribution in 2 dimensions, which is just the area underneath that line. Conditioned on a particular, so the distribution underneath that curve in 1 or higher dimensions is uniform. And if we take a slice through that resulting volume with a uniform density across it, the distribution on that slice will itself be uniform. So we've kind of taken our original potentially complex target density and reduced it down to a uniform distribution across some geometric object. And then we're saying basically that we can consider projections of that volume onto various different subspaces. So the kind of easiest and most well-known example of a size sampling method is this kind of linear size sampling method, where we basically define some line through space in our target space. We can parameterize in this various ways. We could define the line as just being axis aligned, so we could do a slice sampling update to each of our coordinate axes at time, and something like a kind of coordinate-wise Gibbs type update. Or we could just randomly choose some direction in space, so some v vector, say, sampled from an isotropic Gaussian. But basically, we need to parameterize a line in space that passes through the current point and then somehow progresses through this target space. We sample, given our current point, a value for this h variable between 0 and the current density, which defines the slice. So the slice is basically all of the points which have a density which is above the value of the slice variable. So all points from here to here have a density which is higher than h. So within a, say, if this was a cross-section through a distribution defined on a 2D space, the slice variable the slice itself might look something like this. We then define, as I said, some line through our target space. So we have the slice, which is this orange object, and then a line through space. And what we want to do is find the portion of the slice which intersects with that line. So if we could exactly solve for that intersection, and so if we made some assumption about, say, our distribution being concave, so that this slice had a nice, simple concave form, then we could potentially exactly solve for the intersection with some line, and then exactly sample from that resulting uniform. In general, we're not going to be able to do that because we're not going to make these assumptions about the geometry of a distribution. And in fact, this slice might not be some simply connected component. It could be a series of non-connected components dotted across space, particularly, for example, if I sliced, say, here, we can imagine having 2 distinct slices here and here. But what we want to do is basically find some intersection which is as large as possible between that slice and the line we've defined through space. And this is a bit at which we move from this kind of general description of slice sampling to the very kind of elegant and specific construction that Radford Neal came up with for defining an algorithm for doing that in a way that's kind of correct and that it leaves the overall distribution of interest invariant. So in this 2003 Annals of Statistics paper, there are various different ways of kind of constructing that bracket, which are this kind of intersection of the slice with the line, which are kind of considered. The most simplest initially involves what's called a linear stepping out. So we take our current point and some bracket width, which I'm just for simplicity going to consider as the kind of length of this arrow here, and then randomly forward and backwards along this line, I kind of expand out some bracket. So initially, I position the bracket uniformly around the current point. So if it's of width w, I might say position it here. And then I sample some Bernoulli variable to say if I'm going to go forwards or backwards along this line. I add on a segment of equal length to the initial bracket. And I keep doing so until basically I extend outside of the slice. So I reach some points, say, here and here, so that how I test that I'm at the slice, I just compare the density at that U point to my slice variable and see whether or not I'm above or below it. So if I imagine this dotted line is now that resulting bracket as a result of that expansion, the next stage of slice sampling is then to sample uniformly from the intersection between that slice and this line. And how we do that is basically we just initially propose some variable uniformly from that whole bracket from here to here. For example, this red point. If it lies on the slice, we would accept straight away. If it doesn't, we basically have this recursive procedure where we shrink the slice such that the current position remains on the slice bracket, and that we get rid of some portion to one side of the last rejected value. So from here, we would say shrink to this bracket. And then we, again, sample uniformly from that shrunken bracket, which we can kind of see is going to have this kind of geometric or exponential type scaling such that it will get smaller quite rapidly. So now we say we might sample this purple value that's now within the slice and we'd accept that value. So there's this kind of two levels of adaptivity within the slice sampling algorithm. So there's the initial expansion of the slice bracket by doing this stepping out. And so I described this linear stepping out method, which is the simpler. There's also what's called the kind of doubling method, which instead, rather than stepping with increment equal to some fixed bracket width, instead we always double the size of the current bracket. So we can see that that would, if we'd kind of misspecified this initial size quite badly, it would much more quickly bring us outside of the slice, and so we would in some sense be more efficient because we're requiring fewer density estimations. So there is a valid way of constructing that. It's a little bit more subtle to ensure reversibility. In practice, in some distributions, that can help a lot if you've got very varying scales, and you would struggle to come up with some summary of a kind of typical scale to set this initial slice bracket width. But it's worth kind of strongly emphasizing at this point that although this is a free tweak parameter setting this slice bracket width, whether or not we use the doubling or stepping out procedure, because there is both this adaptivity of potentially expanding that, but then also once we do the kind of recursive slice shrinking, shrinking that down to a more local proposal, the overall algorithm in terms of how far we actually move is fairly insensitive to the choice of that slice bracket. What is potentially sensitive to the choice is the number of density evaluations we have to do. So we set a far too small slice bracket and then we insist that we get outside of the slice, then we'll have to do lots of steps outs to do that. So that would be inefficient. But correspondingly, that's still better in some sense than choosing a too small Metropolis Hastings move, where we would have this kind of diffusive effect where each individual move would still be small, and we wouldn't have this coherency in kind of motion, because in this high-dimensional setting, we would have this kind of random hawk type behavior. So The bracket width is important to some extent, as in there are definitely extremes which the slice sampler will become inefficient. But compared to, say, the proposal width in a simple random walk metropolis method, it's a much less kind of key parameter, and it tends in practice to be quite robust to the choice of these values. Okay, so far I considered kind of slice sampling in a very unconstrained space. A key issue in the sort of problems we're interested in might be that the distribution of interest might be defined on, say, the hypercube. As a kind of trivial construction, we know that all of the random numbers generated in a pseudo-random number generator at some level come from uniform random draws. So we could, in that earlier description of unbiased estimators, have made a simplifying assumption that the auxiliary variables are all uniform variates, and then kind of collapsed all of the operations, things like rejection sampling, inverse transfer sampling, which then take those uniform variates and produce from the various distributions of interest. So this will often not be what we want to do. Those transformations might have fairly nasty properties. Things like rejection sampling will require a varying number of samples and will be non-differentiable. But more generally, often we know good ways of generating distributions from samples from distributions using uniform variates, using things like inverse CDF transforms. So often we will have problems in which we can easily express the auxiliary variables used within an estimator as uniform variates. And then we would, if we want to update those variates using slice sampling, we need to be able to somehow define a slice sampling transition within the hypercube. And the key issue here is obviously going to be dealing with the boundaries of that hypercube. So the simplest way we can perhaps do this, and this kind of relates to an idea within that 2003 paper by Bradford Neal again, of something called reflector slice sampling. So reflection as an operation, so if we kind of reflect through the normal of some surface, is a reversible operation. And we can kind of apply that in a very simple way when the surface we're reflecting on is this kind of axis-aligned hypercube as we have here. This is just going to be some very simple arithmetic kind of modulo operation on a computer. And basically then rather than just defining a path which continues indefinitely in space, we define a path which at every intersection with one of the boundaries of the hypercube just reflects. And we can kind of do that implicitly by just kind of stepping through and, as I said, doing this modulo reflection operation to compute values to kind of reflect them back inside the hypercube. And then we just run a standard slice sampling algorithm as we had before. So if we imagine we've already expanded out this bracket to have these two endpoints outside of the slice, we then propose a point on it, and then repeat and recurse again until we accept a point within the slice. So this reflective slice sampling variant we'll kind of use in some of the experiments that I'll go on to discuss in a bit. So another slice sampling variant which was proposed, which has been proposed, is this elliptical slice sampling method by Ian Murray, Ryan Adams, and David Mackay. So the idea here is rather than looking for the intersection of a slice and some linear path-free space, we instead look at the intersection between an elliptical path and the slice. And so why an ellipse? Well, if our distribution was exactly Gaussian, then we can define ellipses through space such that if we were to uniformly sample any point on that ellipse, we would, if we were originally Gaussian, we would be, with some mean covariance, we would be exactly Gaussian after that transition. So it would exactly leave that Gaussian distribution invariant. So if we believe that the target distribution is in some sense well approximated by Gaussian, so that could be we have a strong Gaussian prior, so this often comes up in, say, Gaussian process models where the Gaussian prior this kind of high-dimensional space might be the main thing kind of informing the posterior on a lot of directions in space. Or perhaps we've come up with some, say, variational Gaussian approximation to the posterior that we think at least locally fits that posterior well. Then basically we can kind of think of redefining the density, say, with respect to the Lebesgue measure for the distribution as with respect to the kind of Gaussian measure defined by this Gaussian density. We now have, as I kind of described, this kind of elliptical update will exactly preserve the underlying Gaussian measure. And then all we need to account for is the kind of density ratio between that Gaussian measure and the actual target measure of interest. So if, say, this is a variational approximation, this will be the kind of residual kind of ratio between that variational approximation and the actual target distribution of interest. And so now we've kind of performed slice sampling in that Gaussian space. So a nice thing about the elliptical slice sampling algorithm is that it eliminates even this initial bracket width parameter that I discussed in the linear slice sampling case. And that it also has this nice property. So at least in the kind of linear stepping out kind of canonical variant of slice sampling that I described, we need to at least evaluate in most, if initial bracket is within the, if our initial bracket is within the slice and we expand it out, we're going to have at least a few density evaluations as a kind of overhead before we start being able to accept proposals. This elliptical slice sampling algorithm, because it doesn't have this initial expansion stage, is basically able to accept proposals straight away. And because it has this kind of Gaussian prior preserving property, actually, in practice, if your distribution is close to Gaussian, it will often accept a near to independent point and accept that straight away with one density evaluation. So it will perform very similar to, say, doing a Retropos independence proposal, while still having the ability to back off kind of in this recursive fashion to these more conservative proposals if that initial independent proposal or near to independent proposal is kind of untenable in terms of being off the slice. And so we can see straight away that this is the sort of property we might want for a Markov transition operator defining on, say, these auxiliary variables in a density estimator, so that we can kind of take this plug-in replacement for say, independent sample from some Gaussian distribution on those auxiliary variables. So we often might have, say, auxiliary variables which are standard Gaussian variates. Rather than independently sampling from that standard Gaussian prior, we could use the elliptical slice sampling step, which at best, if that Gaussian prior is a good approximation to the posterior, will tend to produce near to independent samples. But if that's not the case, it will still be able to make some local move in space and not have this kind of pathological rejection. So yeah, there's some more details of the particular algorithm here. So as I said, we kind of define an ellipse through space. We specifically parameterize that using some kind of angular theta parameter. And so how we define the ellipse is that we sample some auxiliary variable from the normal distribution of interest, and then the combination of that auxiliary variable, our current variable, and then this kind of functional form which parameterizes an ellipse in space defines the path for which we're going to do slice sampling. So this form here, for those who are kind of familiar with Crank-Nicholson type updates, so the kind of equivalents under various different names in a kind of Metropolis-Hastings sentence, should be familiar. So sometimes we instead say parameterize this cos theta is some correlation parameter rho, and then a sine theta would be the square root of 1 minus rho squared. But basically, we can think of elliptical slice sampling as a adaptive variant of a Crank-Nicholson type update. So we, rather than setting this rho as some fixed value, we adaptively set it to try and be close to independent as possible, but kind of conservatively reducing down to more and more correlated if that initial independent proposal is not valid. Okay, so yeah, as I said, how am I doing time? Okay, I'm going to skip over the details here just because the kind of actual implementation of the algorithm ends up looking a lot like that initial linear slice sampling algorithm, just with some tweaks to this kind of elliptical geometry. And kind of move on to actually considering how we might use these algorithms in practice. So within this auxiliary pseudo-marginal framework, it's, as I've kind of been pointing out, it's natural to perhaps consider using slice sampling algorithms for these two different transition operators. So we could, say, slice sample these auxiliary variables. So there are two common cases, or even might be a mixture of these two cases that we might have. So we might have a vector of independent uniform variates. As I said, often estimators can be kind of parameterized in terms of independent uniform variates. Or we might instead have a series of standard Gaussian variates. And either of these two cases are quite natural choices of either this kind of reflective linear slice sampling within the hypercube or this elliptical slice sampling on that standard normal prior that we could apply in that case. And in both of those settings, there's kind of minimal tweak parameters. So elliptical slice sampling has 0 tweak parameters if you kind of ignore this hidden tweak of coming up with a good Gaussian approximation. Linear slice sampling generally has this bracket width, but in the kind of uniform hypercube case, we can often just set that fairly we can set that with a fairly rough heuristic, as say being equal to the unit interval, such that we're on each and then sample a direction from a uniform distribution, such that we're basically taking the some sort of modulo operation between a independent uniform variate and our current state as our initial proposal once we kind of reflect through the hypercube. So we could also consider slice sampling the z variables. We wouldn't actually be able to do this, or at least it would tend to not work well to do this within a standard pseudo-marginal setting, because the kind of key assumption of slice sampling is this slice is constant through the course of the algorithm. And if we were using the stochastic density estimator, then the density estimate would vary over time, such that whether or not we're on the slice would be affected by the stochasticity in that estimate. And this kind of noisy slice sampling tends to, in practice, even though you can show it, does still leave the correct distribution invariant to perform very poorly in practice, because this kind of conservative backing off will tend to reduce down to a very quick level, down to a very local proposal very quickly, and so you lose a lot of the good properties of slice sampling in these kind of smoother, more standard settings. But within this auxiliary pseudo-marginal method, we've kind of factored out the dependence on u and fixed the u within the updates to the z, and so that's no longer a problem. So just to kind of point out that this whole auxiliary pseudo-marginal framework, and in particular some of these kind of ideas of applying elliptical slice sampling within pseudo-marginal methods, is very closely related to kind of concurrent work by Giannadis et al. And Allen et al. On these, this kind of what I'm using here as an umbrella term of correlated pseudo-marginal MCMC methods. So these two papers appeared on arXiv in a very short period, and both propose basically the same type of transition operator within a pseudo-marginal method, and then actually, as I've pointed out, the particular form of update, which is a Crank-Nicholson update on the auxiliary variables, is quite closely related to the elliptical slice sampling variable algorithm that we propose to use in the pseudo-marginal slice sampling paper. So they make the strong assumption that the auxiliary variables have this prior normal distribution, but under that assumption, we can define this Metropolis Hastings kernel using this Crank-Nicholson type update. here now parameterized in terms of this row variable, such that this would exactly leave that Gaussian prior invariant, and then we just need to adjust for the kind of, as I said, the remaining density ratio portion of the target density of interest, which here boils down to the density estimator. So this kind of form of update, again, looks like a lot like the actual acceptance probability, looks kind of identical in some sense to the standard pseudo-marginal metropolis Hastings. So rather than doing this separate update of the Z and U variables as in this auxiliary pseudo-marginal framework that I discussed previously, this jointly updates the U's and Z's, but updates the U's such that it exactly preserves the Gaussian prior, but correlates the U dash and U. And in practice, this kind of coupling between the density estimates tends to improve the performance of the overall metropolis Hastings kernel. So there's been a whole series of work looking at extensions of this, and we'll discuss some of it in the next part. But yeah, this correlated pseudo-marginal Mcmc type idea has come up in various forms, in various ways, among lots of different research groups. And so I'm not claiming any particular originality in the particular methods that we're looking at. Our focus was more on, could we come up with something that is useful in practice in the sense of having a kind of high degree of robustness and a lack of free parameters that need to be tweaked to get it to work well. Okay, so I think I'll round up there because it's time for the break. There was a few experimental results that I was going to cover in this part that I'll just put into the next section. But if anyone has any questions, feel free to. So the elliptical slice is, I didn't make that very clear. I realized that I only kind of described very laterally how it was parameterized, but it's naturally defined by the Gaussian approximation of Gaussian prior. So you generate an ellipse by, you have some, if you take the vector from the mean of the Gaussian and your current point, and then you generate some variable independently from that Gaussian, something like this. So again, that will tend to be centered around the mean with some random direction. And then those 3 points uniquely define some ellipse free space. And then what you're doing via this theta variable is basically modulating how much you're going to depend upon x and how much you're going to depend upon, say, this v in the eventual outputted sample. So if theta was equal to 0, so cos theta is equal to 1, you would basically not move at all. If theta was equal to pi over 2, you would exactly output an independent sample. So it's just a way the ellipse itself isn't some kind of geometrical construct you're having to really strongly think about. It naturally comes out of the Gaussian geometry. That said, defining what Gaussian to use is not necessarily always clear. So people tend to use the prior, but if you have a strong likelihood, that prior might not be a very good Gaussian approximation to the actual posterior. So in that case, this whole idea of you're preserving the prior, but that might not mean much in terms of actually defining a good move in the posterior space.
Any other questions?
What's the relationship between this elliptical slice sampling and just doing HMC with a Gaussian?
So if you were to, so there's been quite a few papers on making these sort of links. And particularly in the Gaussian case, because we know the analytical solution for the Hamiltonian flow, and that exactly corresponds to, the isopotential surfaces or ellipsoids. If we were to project onto some plane through space, so we're kind of to limit our momentum such that it's on some linear subspace, then the Hamiltonian flow would describe an ellipse. In general, it won't, as in like we might have some more complex path across the surface of the ellipsoid in higher dimensions, but at least in 2 dimensions, we would exactly trace out an ellipse. In higher dimensions, it will be some periodic path across the surface of an ellipse, but we could always consider to say updating one variable and its conjugate momenta, and that would give us some ellipse-free space. And then we're kind of, the slice sampling then, choosing this theta variable, is choosing the integration time of the, yeah, and that's why it then feeds into things like nuts, where we use a similar idea to, rather than varying a continuous theta parameter there, we choose a discrete number of integrator steps, but using a slice sampling type method, at least in the original nuts formulation.
So the spirit is exactly the same?
Yeah, it's just you define some linear trajectory through space, parameterized either by a continuous or discrete variable, and then you somehow slice sample along that trajectory, using that as the kind of slice variable that you're updating and defining a bracket on.
Okay, so let's thank Matt again.
Would that correspond to using, say, what people call the fish identity? You just push that in.
So I definitely it is used definitely within showing the equivalence of Fisher information in terms of the Hessian and the product of Jacobians. As much that, so I don't know if that in machine learning definitely gets called the log derivative trick or the score function.
Yeah. So the second one that you talked about is the
path derivative.
Is the reparameterization trick.
Yeah. So that actually has links to what Neil was discussing, in as much as that you can kind of think of it defined some, you're kind of factoring out some of the distributional transformation in terms of this deterministic function, which is defining kind of some flow through space, and then looking at the gradient of that deterministic operation, and typically that leads to...
Is it provably lower variance?
In certain cases, yes, but it does depend on, I think beyond fairly simple target distributions, I'm not sure if there's much
theory to back it up.
Yeah, definitely in practice, that's basically why all of these stochastic gradient descent methods for variational inference moved from being a kind of fairly small part of, I think, the variational inference world, where more typically was using these kind of coordinate ascent type methods and so on, to definitely machine learning. Once people start using these reparameterization type estimators, it was just